So rates of change are such a large basis for a lot of what we do in calculus. It's finding this instantaneous rate of change that's occurring at the function at a single point. So where we start that conversation is with average rate of change across two coordinates. Our next step that we're trying to work in here is this idea of a difference quotient, which instead of thinking of two kind of just distinct points, think of a single point and then another point that's a certain distance away. Because then our goal is to shrink that distance down until we're essentially at one point. So it's this little side step that we're doing. And what I'd like to do in this video is talk about these two rates of change, how they come through in a function in similar ways. They're calculating the same thing essentially. But really the purpose of this video is to get into Desmos so that it can set up tables for us so we can evaluate trends of things to kind of speed along those calculations. So I'm going to try to keep this video as short as possible to kind of get into Desmos and setting up things and calculating, because that's what you'll be doing in your homework and assignments. But I have already made another video of this where I go through each of the questions in a lot more detail. It just ended up being quite a long video, so I wanted to make a quick one. So if you just want to get to kind of the heart of it, you can with this video. But I'll also link the other video if you are interested in more detail. Okay, so average rate of change, just visually these two things are going to be the same, but the idea is that we have some function, let's say it's a parabola in this case, and if we graph 2 points, we want to find the rate of change between those 2 points. So for average rate of change, we take the difference in the outputs over the difference of the inputs, which finds the slope between those 2 lines, or 2 points rather. Now, what we're changing with difference quotient is that we're fixing one of the points. So let's call one of these just x and f of x. And what we would do is describe the second point by the distance it is away. So if we have this distance of h, then the second point, our x-coordinate would be x plus h, and then our output would be f of x plus h. So with that, we're linking to this kind of stationary point that we set, and then we have what eventually will be this kind of moving point as we move that distance to 0. So let's talk about these two ideas in the context of this application with the population of bees, and our function that we're going to be using throughout this is 32 minus 2t squared, which is mapping the population of the bees. So we're going to skip down here to part B and C. So in part B, it says to write and fully simplify the formula for the average rate of change for B of t over the interval t0 to t1. So what I just want to point out here really is that we're looking at two different x values, essentially, or two different input values. In this case, it comes through as two different points in time. So with that, we take the difference in our outputs over the difference of our inputs. Now, what we're going to do in the next step, as we start kind of trying to calculate this instantaneous rate of change, is that we want the interval, or rather the distance between these two, to get closer and closer. So where we're headed in part E, jumping way ahead, is we want to know, what if we wanted to know the rate of change that was occurring exactly when t equals 3? So what we could do with that is instead think of our interval as having an input of 3 and then another value for t that's a value close to 3, and we want to see what happens as we make t closer and closer to 3. So like the closest could be a 2.999999, something like that. But we want to evaluate the trend as we get closer. So if I jump down to part E real quick, that's what this left-hand side of the table is doing, is we're setting our value for t to be 3 for one of them, and then we want to see the trend as the second value for t gets closer and closer to 3. So in the middle here, this is where we have 3 coming through for the second value of t, but we can't plug that in, because if we did, and we're taking the difference of these values, In the denominator, we'd get 0 out, and that's going to give us something undefined. So instead, we want to evaluate what's happening around it. So what we're going to do for this example is we're setting t0 to be 3. And then we're setting up a table so that we can change values for t1 and see how that occurs. So this is our average rate of change. Let's focus on this for a second. And what we're going to do is go into Desmos so that it can fill in this table for us in a nice quick way. But with that, it takes a little formatting, so that's what I want to really teach you in this video. So in Desmos, what we're going to start with is we always need to start with defining our function. I always just opt for f of x, even though we're working with b of t here. Sometimes Desmos can get funny about using different letters, but f of x, it knows how to do. So we would go 32 minus 2x squared, and with that we have our function defined. It'll even give you a nice little visual of the graph as you work through it. Then what we're going to do next in the next line is create a table. So with that, I'm going to click this little plus item, the add item, select table, and then for x1, I would plug in all my values for t1 into the table. And just save a bit of time, I have that all set up on this next screen here, where I have all my values for t1 as part of x1. Now nothing's filling in on the right-hand side, and what we need to do is define the relationship, and we're going to use that with this format for our average rate of change. So what we're going to do is I'm going to delete that y1 out of there, and I'm going to set up a fraction. So I'm going to start with my division symbol, and that's going to set up my numerator denominator. So for the first function output, what I want to be doing is taking these values for x1 and plugging them into f of x. So typing that, I'll go f parentheses, and then for x1, all you do on your keyboard is type the letter x and then the number 1. It automatically formats it for you to that little subscript of 1. I didn't have to do anything special. So just x, then 1, and close those parentheses. So that's going to grab those values, plug it into our function, and then we're going to subtract away f of 3. So f parentheses 3. That's going to stay the same for each of these. And then the denominator, I'm going to use my values for x1. So I'm going to go x1, and then we're going to go minus 3. And with that, it'll fill in my table. And what I can see is over here on the right-hand side, the values are getting closer and closer to negative 12. And then same thing on kind of above t equals 3. If I get closer and closer to where 3 is occurring, they're approaching negative 12. So what this is showing me is that as we close the distance between those two different times, we're approaching an average rate of change of negative 12. In this case, what it would be, it's decreasing by 12,000 bees per month is what we're seeing there. So that's average rate of change, taking 2 times and then shrinking down how close they are together. So for difference quotient, let's go back up here to part C, where we have our formula for difference quotient. And with this, what we're doing is our interval is basically having a value for t, and then t plus some distance away. So that's what h is representing here. There are different ways to explain it, but how my mind kind of grasps it is like h is a distance away from t. And what we want to eventually do is shrink down that distance into 0. But with the format of the equation right now, if we plug in 0 for h, again, that denominator is going to become undefined and it all kind of falls apart. So that's where we need to set up this table to see what are the trends showing. So using this format, we want to plug in b of t plus some distance, and then we'll subtract b of t, and then we want to divide by that distance. So going to our table, what we're going to do is set it up so again, t is stuck. T is stuck at a value of 3 because we want to see what's happening really close to 3. And if h is our distance away, so like this is 1 unit below, half a unit below, a quarter of a unit below, we're getting closer and closer. So we're essentially approaching to the point where h equals 0, where we have no distance, but we just can't plug that in. And then same thing above, we're just a little above 3, a little further away. And we want to see just what's happening from this side as we get closer and closer. So we want to see what are we approaching from both sides on this table here. So plugging in, if we're thinking of this b of t plus h minus b of t over h, what we're doing is we're setting t to be equal to 3. So that's a value that's going to stay the same for each of these, and then h is going to be my variable that's changing value to value as we go along the table. So let's go into Desmos, and I have this table set up. So I have my function f of x again, and I set up the table so that I have these distances that are approaching 0 from above and below. And now what I'm going to do is define my function. So I'm going to set up my fraction, and first I want that b of 3 plus h. In this case, it would look like f of 3 plus, and then I want to be plugging in my value for x1. So I'm just going to type in x1, close those parentheses. And then I'm going to go ahead and subtract f of 3, f parentheses 3 parentheses, and then that's all going to be divided by h, which in this case is our value for x1. And what I can see is a similar trend because this is calculating the same thing really of what's its rate of change. In this case, it's that we have 2 points and they're still getting closer and closer together, but it's defining it as that distance away of h being 0. So we're seeing that trend of it approaching negative 12 from above and below, just like we saw with average rate of change. So just to summarize, so with Desmos, we can use both of these methods, but more and more we're going to move towards this difference quotient idea of setting up the table. But just to write down the notation I used within Desmos, so in this case, we set it as 3. So first thing we do is we define our function, whatever that might be. Then we take the value that we're setting for x that's going to be stationary. And in Desmos, where we have our y values, we set up a fraction. And in this case, we're going to take f of the output, x1 minus f of 3 over x1 minus 3. Or you can switch the order of those, and that's completely fine with that one. With this one, though, the order does matter, and we'd want to take f of, and then where it would be x plus h, we're setting x to be always 3 in this case, and then we'll go plus x1, and then we're going to subtract f of 3, and then we'll divide that by x1. So that would be the format we can use in Desmos to set up those tables. Now, you have the functions. You don't have to use the tables. It just speeds things along, so it'll fill in everything for you at once. So you just have to set it up one time, but you can use a calculator individually with each of these and plugging in the values, and you'll get to the same spot.